Okay, so this is lecture 26. We're going to be talking about the time it takes to get to an absorbing state. So one of the things that motivated this is our example that we did on graduation. So we talked about how students, when they're in a university, then there's some % chance that they might drop out or they may graduate. And so these are what are called absorbing states, because in this Markov chain, we're assuming if they drop out, they are not coming back, and if they graduate, then they're not coming back as well. So these are our absorbing states in this example. So last time we calculated the long-term long-term probability of being in one or the other one of these states, and so here we looked at this red one was the probability of dropping out, and the green one was the probability of graduating, and these depended upon whether or not I was a freshman, sophomore, junior, or senior. So which class they were in at the time is how likely they are to get to one of these two absorbing states. So what we want to talk about in this lecture is how long it takes to get to an absorbing state, so the expected time to absorption. And if, like in our graduation example, there's more than one absorbing state, then what's the probability of being in one of the absorbing states versus the other one? So obviously in the graduation example, we'd much rather have students graduate than to drop out. Okay, so let's consider this example here with this probability transition matrix. So here we have 4 different states. So if we think about this, what is an absorbing state? So how do you tell if you have an absorbing state? Well, basically it means if you get in that state, then you're going to stay in that state forever. So where is that in this probability transition matrix? Well, let's just look at our transition diagram for this, and it kind of helps us to see. So here, our absorbing state is state 2. So if we're in state 2, we have 100% probability of actually returning to state 2. So this is our absorbing state. You can see that if you look at the matrix, because it would have a diagonal element, which would be a 1. So if you have a diagonal element, which is a 1 here, then this is our absorbing state. So in this example, we have one absorbing state. And so just a little bit of facts about it. So we have 3 different classes. We have one with just a 1 in it, one with a state 2, and then 3 and 4 are communicating, so they're in one by themselves. Everything else is transient except for 2, which is recurrent and absorbing. Okay, so the first thing that we really want to do is we want to reorder this matrix. So we want to get the absorbing state kind of by itself so we can kind of tell what's going on. Okay, so we're going to think about partitioning the matrix P into K absorbing states and M minus K transient states. So here we only have one absorbing state and 3 transient states. So we can reorder this matrix so that we have basically the one up here or the one down here. Those are the easiest ones to consider. So in this example, I have put the absorbing state up here, so we just reorder them. So if we reorder the top by 2, 1, 3, 4, you have to reorder the other 2, 1, 3, 4. So we have now the probability of going from 2 to 2 is 1, 2 to 1 is 0, 2 to 3, 2 to 4, etc., etc. So it's the exact same Markov chain, just the matrix is reordered because the states are reordered. Okay, so in general, the way that we want to think about reordering this is so that we have an identity matrix somewhere that has our transient states, and then we have zeros below that identity, or in some cases above the identity. And then we have other parts of the matrix that are labeled A and T. So in this case, this would be our identity, this would be our zeros, this would be our A, and this matrix down here is our T. Okay, so if you have some state that's a transient state, then and I is any state in the Markov chain, then basically if you're talking about the probability of going from I to J in n steps, as n goes to infinity, this goes to 0 because J is a transient state. So you're going to eventually go out of that class. So eventually you won't return. Okay, so we're going to let T be the submatrix of our probability transition matrices, where we have J and K are transient states. So now what we have, based upon this identity here, we have the limit of our T matrix, a limit of our T to the N matrix goes to 0 as n goes to infinity. So now we introduced what's called the fundamental matrix of discrete time Markov chain theory. So we're going to let new j be a random variable for the number of visits prior to absorption to state j. So then we can talk about the expected, the mean or the expected value of this random variable. So now this is the number of visits prior to going to an absorbing state. And we can write this as I plus t squared plus t cubed, etc., which is reduced to this identity where we have I minus t, and we take the inverse of that. This matrix here is called the fundamental matrix of discrete time Markov chain. So now we can use that to get what's called our expected time to absorption. So this f was what we just looked at previously. This f is the inverse of I minus t, where t is just that one portion of our probability transition matrix. And our expected time to absorption is basically, if we sum up all the columns of f, it gives us the expected time to absorption depending upon which stage you start in. So going back to our P that we had, so this is our reordered matrix because we have this 1 up here in the corner, so this was our reordered matrix. What we can do is we can think about separating this. We can pick off our T and we can form our fundamental matrix. So once we have our fundamental matrix, remember what these are. So this first column of our fundamental matrix corresponds to state 1, state 3, and state 4. These are our transient states. So if we sum up the columns, we get the expected time to absorption. So here what we see is if we begin in state 1, then the expected time to absorption is in 2 time intervals. So let's see if that makes sense. So here 1 can go to itself, or it could go to 2. So yeah, that seems to make sense. Beginning in state 3, then the expected time is about 6 time intervals. So here 3 has to go all the way around before it gets to 2, so you can expect that it would be a little bit longer than obviously it would be for 1. In state 4, it doesn't even have to go near as far, so the expected time is only 5 time intervals. So it makes sense. Okay, so now if we think about the expected time to absorption for our graduation example, again, what we can do is we can split this up, and so here's our absorbing states down here, dropout and graduation, and then we can pick off our T. So this is just the MATLAB code. So if you have your probability transition matrix, you pick off the T by saying which rows you want, which columns you want. So here I want the 1 through 4 rows and 1 through 4 columns. Once I have that, I can find my fundamental transition matrix. So remember that was the inverse of I minus T. So here this I forms the identity matrix, and this 4 by 4 comma 4 gives the size of it. So since our T is 4 by 4, we want our identity matrix to be 4 by 4, so we have I minus T and take the inverse of that. Here we get our F. So now we can sum up those columns. The other way of thinking about doing this is, remember, we can say our M is those 1s, so this is a vector of 1s. It's 1 row, 4 columns here, times our F, same as if we just summed up our columns. So this is our expected time to absorption. So what this says is basically what you would guess. It's approximately 4 years. So here, if you start as a freshman, remember this is freshman, sophomore, junior, senior. So if I start as a freshman, it's approximately 4 years to absorption, approximately 3 years for sophomores, 2 years for juniors, and 1 year for seniors. Well, this makes sense because our dropout rate is so small that what you expect to have happen is that you expect them to actually graduate instead of dropping out. And so it makes sense that this is somewhere around 4 because it takes about 4 years for freshmen to graduate. About 3 years once you're a sophomore, about 2 years once you're a junior, and about 1 year once you're a senior. So this makes sense. Okay, so now this is an example about gambling. And so part of this is what we're going to do here. And then another part is you can do it as an optional assignment. So I've decided to make this week's assignment optional. which means that you can either choose to do the assignment and get extra credit, or you don't have to. But it's based upon this example, and the optional assignment also has one about umbrellas, which we talked about in the previous lecture. Okay, so in this example, you have somebody, Smith is in jail, and he has $3. He can get out of jail on bail if he gets $8. So there's a guard that agrees to bet with him. If Smith bets $8, then he wins $8 with probability 0.4, and he loses $8 with probability 0.6. Find the probability that he wins before losing all of his money. So we have two different strategies here. We have a timid strategy and we have a bold strategy. Timid strategy is the one that I'm going to do in this lecture, and then the bold strategy is what is optional for homework. So basically this is, he bets $1 each time. So if he bets $1, he can either win $1 or he can lose $1. Now this one, the bold strategy, he bets as much as possible. So if he starts with $3 here, then he's either going to win $3, so he's going to go up to $6, or he's going to go down to $0. So the bold strategy is much bolder because he bets as much as he can. So now if he's up at $6, he bets $2, right? So here he bets as much as he can without going above the amount. So here, this is the optional homework. So what we want to do is we want to find the mean time to absorption for each strategy, which is a better option for him to get out of jail, and then we want to plot it using MATLAB. Okay, so here he starts with $3. He can either win $1 or lose $1. So he can either win $1 with probability 0.4, lose $1 with probability 0.6. So now if he's at $2, again, he can either bet and win $1 or $2 or lose $1. So now the bold strategy, there's a difference, because with the bold strategy, if you're starting with $3, you're either going to go all the way to 0 or you're going to go all the way to 6. So the bold strategy is different. So in the optional homework assignment, you're going to have a different transition diagram. You will not be using this one. Okay, so here is our P matrix with states, starting over here with state 0 all the way up to state 8. So notice, where do we have the ones on the diagonal? We have it here and here. So 0 is an absorbing state and 8 is an absorbing state. So our T is this kind of in the middle matrix. So again, this is our T, which if we have our probability transition matrix in MATLAB, we can pick off our T. Once we've picked off our T, we can find our fundamental matrix, and then we can sum up the columns. So here is our M, our summing up the columns. So now remember, we really aren't interested in all of this, right? So this is the probability that if I start with $1, $2, $3, 4, 5, 6, 7, you know, what's the expected time to get to an absorbing state, the mean time to get to an absorbing state. What we're really interested in is, it already says we start with $3. So we don't care about really any of the other ones. So about 11 times betting, he's going to get to an absorbing state, either to 0 or to 8. So how do we get whether or not he goes to $0 or $8? Because that makes a big difference. He either stays in jail or he doesn't in this example. So here we form a matrix A and a matrix B. So here, remember what this was. This was the 0 state. So this A, it corresponds to probability of the transient states going to $0. And B, here, this corresponds to my different states going down here to $8. So the probability of the transient states going to $8. So if I want to figure out the probability of absorption in different states, I can do A times F, which gives me the probability of going to 0. B times F gives the probability of absorbing in $8. Obviously, we'd rather be here. Or if you're the person in jail, you'd rather be there. Okay, so here is our A matrix. This is how we can get it off of our P matrix in MATLAB. So this is our A matrix. We can take A times the F that we've already calculated. So we have this. Notice here the one that we're interested in is if we start at $3, so the probability of the gambler losing all of his money is about 90%. So we can do the same thing for the blue matrix, and obviously these should add up here. So the probability of a gambler winning enough money for bail is about 10%. Okay, so now we were asked to plot this, and so this is a MATLAB code that is on D2L. This goes through basically what it does. It sets up the space, it clears everything out, it does our probability transition matrix, so it sets it all to zeros to begin with, and then fills in only what it needs to. This is just used for plotting. Okay, so this first part of the matrix actually plots different scenarios. So basically it plots what would happen on a given bet. So you bet $3 and then you have some probability of losing it. So you have 60% probability of losing it. So you have this random number, you have 60% probability of losing it. If you lose it, then you go down by $1. Otherwise, if you don't lose it, you won, so then you can go up by $1. In the bold strategy, you would go down by however much you already have. So you would get down by this entire amount. So if you lose, you're basically going to be at $0, and if you didn't lose, then you're going to be up by however much you bet. So this just plots my different strategies, and then I also plot the probability that after a given bet that I'm more likely to be at 0 or more likely to be at $8. So to see these plots, here I have different colors for different possibilities. So here is one possibility. This is this green one. So I start with $3. I can go up here to 4, to 5, to 6, to 7, to 8. So this would be really lucky, right? So this would be the unlucky one. So I could go from 3 down to 2, down to 1, down to 0. Or I could do something like this purple one here. So I could go from 3 down to 2, back up to 3, down to 2, down to 1, back up to 2, down to 1, and then finally down to 0. Or I could do something that is more like this green line here. So this green line, and I'm not exactly sure where it comes from. It could come from down here, or it could come from this one. I'm not exactly sure which one this green line comes from, but let's assume, so here I could go to 4, down to 3, here up to 4, up to 5, up to 6, down to 5, up to 6, up to 7, up to 8. So different possibilities. Or I could do this pink line here where I go up to 4, and then I go down, 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 up, down, up, down, up, down, up, down, down. So here, after 14, I probably have gotten somewhere. Okay, so now this is the probability. So after I've gone one bet, what's the probability that I'm going to absorb to $0 or $8 after each bet? I have more likelihood of either being at one place or the other place. So this just plots the change in probabilities. Okay, so quickly back to the graduation examples. So here was my M's. This is the mean time to absorption. So now where do they absorb? So this was our probability transition matrix. We want to pick off our A, and we want to pick off our B. So we do A times F and B times F. This gives us the probability of dropping out, gives us the probability of graduating, depending upon whether you're a freshman, sophomore, junior, or senior. These should look very familiar because these were what we did when we did our steady state probabilities. So when we did our matrix multiplication here, and we did p to the 10th power, remember we had all zeros here. This gave us the probability of dropping out, which looks like this, and the probability of graduating, which actually looks like this. So here, there's two different ways of actually finding the exact same answer. Okay, so next time I'm going to talk about the project, which is going to deal more with graduation.